has been discovered that there has been a regular reoccurrence of glacial and interglacial periods over the last 800,000 years. In this episode, I delve into the factors contributing to the cycle. The Earth is mainly warmed by the sun's radiant energy, its primary energy source. To better understand the cause of ice age cycles, it's essential first to grasp the energy balance of our planet. Earth's average temperature is 15 degrees Celsius or 59 degrees Fahrenheit. Earth receives 0.5 micrometers of visible light from the sun. Did you know that electromagnetic waves with a wavelength of 10 micrometers are emitted by our planet Earth? The energy difference between the two is the Earth's average temperature. Do you know how much energy our planet receives from the sun? The quantity measures 342 watts per square meter. Out of the total energy, only 49%, equivalent to 168 watts, reaches the surface. The atmosphere absorbs 67 watts per square meter. 77 watts of energy is reflected from clouds and 30 from firn and glaciers. According to the data, the amount reflected is 107 watts per square meter, while the albedo percentage is 31. Have you ever been aware that the Earth releases infrared and long wavelength energy at a maximum rate of 390 watts per square meter? It's interesting to note that it emits more energy than it receives from the sun. Do you know why the Earth isn't cooling down? The reason is greenhouse gases, such as carbon dioxide and methane. The greenhouse effect, they cause amounts of 324 watts per square meter. In the end, the amount of energy Earth releases is 235 watts per square meter. What happens if no carbon was present in the atmosphere? The Earth's average temperature would plummet to negative 18 degrees Celsius, starkly contrasting the current average temperature of 15 degrees Celsius. Carbon is crucial in warming the planet by a staggering 33 degrees Celsius. It's possible that creating power plants of an unprecedented magnitude would be necessary to raise the temperature to such an extent. As of 2022, the level of carbon dioxide in the atmosphere is only 0.0407%. This translates to 407 ppm. The majority of the air we breathe is made up of nitrogen, oxygen, and argon. Carbon plays a crucial role in maintaining the Earth's temperature at a moderate level without causing it to become too cold. Did you know that almost all carbon on Earth, about 99.94%, exists as minerals? It's referred to as dead carbon. Live carbon exists in the atmosphere, biosphere, and hydrosphere, but only in a small amount of 0.06%. The majority of live carbon, over 99%, is found in the ocean. It's alarming to note that even a tiny quantity of greenhouse gases in the atmosphere can contribute to global warming. Scientists are raising concerns about this issue as even a slight shift in carbon levels can significantly increase Earth's temperature. The sun's radiant energy fluctuates slightly over time due to Earth's orbit and subtle changes in its axial tilt. The primary reason for cyclical climate change is alterations in the Earth's axial tilt. Every 24 hours, the Earth revolves counterclockwise on its obliquity, currently inclined at 23.5 degrees. What would happen if this axle of rotation were perpendicular? The lower latitudes will be hotter than they are now, and the Arctic and Antarctic will be much colder. However, we're fortunate to experience 4 seasons due to the Earth's tilt at an angle of 23.5 degrees while it orbits the sun. Let's change the perspective, fix the Earth, and look at the sun. As the sun passes between the Tropic of Cancer and the Tropic of Capricorn, it provides solar energy to a larger region with lower latitudes. This is also possible because the axis of rotation is tilted. Simply put, the tilt of the Earth affects how sunlight is spread across different areas. This tilt also helps balance the temperature difference between the equator and the poles. It's worth noting that the angle of inclination of Earth's axis of rotation has fluctuated over the last 600,000 years, ranging from 21.5 to 24.5 degrees. These changes occur in a cycle that spans roughly 41,000 years. When the tilt is more pronounced, the difference between summer and winter also becomes more apparent. Currently, our planet's tilt is at 23.5 degrees, placing us in a middle position. The previous highest tilt occurred in 8700 BCE, before the Common Era. The next lowest tilt, when our planet will have its minimum tilt, will take place in the year 11,800. The Earth revolves around the Sun once a year. However, the Earth's orbit around the Sun is not strictly circular. It is a very slightly distorted circle or ellipse. Let's scale the orbit so small that the long side of the ellipse is 30 centimeters, and the short side is 29.996 centimeters in diameter. The difference between the two lengths is only 0.04 millimeters. This slight distortion is one of the causes of the periodicity of the climate. Also, remember that the Sun is not at the center of the Earth's orbit. As in the screen, the focus is on the ellipse long axis and slightly off-center. Because of this, the distance between the Earth and the Sun changes somewhat but steadily throughout the year. Perihelion is around January 3rd, and aphelion is around July 4th. The aphelion is about 3% farther from the Sun than the perihelion. The energy the Earth receives from the Sun is inversely proportionate to the square of the distance. It's worth noting that the amount of energy the Earth receives from the Sun is about 7% higher on January 3rd, during the winter season in the Northern Hemisphere, compared to July 4th, which falls during the summer season. A measure of how distorted an orbit is called eccentricity, and I'm gonna draw it with some eccentricity. And just so you know what I'm talking about when I say eccentricity, a circle has no eccentricity. This ellipse right here has more eccentricity than this circle, which has no eccentricity. And an even more eccentric ellipse would look like this. So you can think about eccentricity as a measure of how far you are from being perfectly circular. So Earth's orbit around the Sun is pretty close to circular, but has some eccentricity. It is slightly elliptical, and I'll exaggerate it a bit in this drawing right over here. So let's say that this is the closest point that Earth gets to the Sun. So that is perihelion. The eccentricity has a value between 0 and 1. If it is 0, the orbit is a perfect circle. If the value is significant, it becomes a more uniform ellipse. The eccentricity of Earth's orbit is 0.017 now, which is very small and almost circular. However, the eccentricity increased or decreased periodically over a long period. The smaller the eccentricity, the closer it is to a circle, the greater the radiant energy received from the Sun. Conversely, as it increases, the energy decreases. Earth's orbital speed is fastest in early January when it's closest to the Sun. In other words, winter in the Northern Hemisphere passes rather quickly. In the Southern Hemisphere, the exact opposite happens. In early January, when the Earth passes perihelion, it becomes midsummer in the Southern Hemisphere. However, it is shorter than summer in the Northern Hemisphere. The direction of the tilted axis of rotation points towards a place in space, wherever it is in its orbit. So regardless of the season, the axis of rotation always points to the North Star in the area that extends straight to the north. Thanks to this, in the Northern Hemisphere, even in unmarked deserts or open seas, it was possible to determine the direction as long as the stars were visible. However, the direction of outer space is changing very little over a long time. It is something called precession, and the best analogy I can think of for precession is if you imagine a top, or the Earth on top of a spinning top. The top is spinning in this direction, and the tilt tells you how much it wobbles. In other words, the Earth's axis itself is shaking and rotating. It takes 26,000 years for the arrow connected from the axis of rotation to follow the rotational trajectory. This precession also affects Earth's climate. Let's look at the orbit again. Its orbit is elliptical rather than real, so many can imagine that this is Earth at some point. Let's assume it's tilted towards the Sun right now. This will be the summer in the Northern Hemisphere. If there's no precession, the perihelion tilts in the same direction. Earth still has the same tilt direction. We still have the same North Star. And now it'll be winter in the Northern Hemisphere. Without precession, it would have tilted in precisely the same direction as it came back to the starting point here. Now, let's consider what happens when there's precession. What happens with precession is that when it goes around the Sun once, it doesn't point in precisely the same direction until it reaches this point again. Let's zoom in more on Earth. It's easy to confuse precession and obliquity with each other. Obliquity is how far we are going from vertical. With Earth at the same point in its orbit, is it still summer in the Northern Hemisphere? Well, it's not because we're not pointing directly right now, we're most inclined towards that point. Now, just with precession, this arrow slowly follows this thin circle year after year. It is now traced out a little bit of that circle. It is now pointing in this direction. And it would actually take thousands of years for the precession to change this much. But here's when we would be pointed most towards the sun. The period has two cycles of 23,000 years and 20,800 years, slightly shorter than 26,000 years due to precession and the effect of the Earth's elliptical orbit rotating little by little in space. But the important thing here is that precession affects the Earth's climate. The current perihelion serves to temper the cold during winter in the Northern Hemisphere. However, after about 13,000 years, when the Northern Hemisphere is in the middle of summer, it will reach perihelion. This will make summers hotter and winters colder. Also, the number of summer days in the Northern Hemisphere decreases because the Earth's orbit speed increases around perihelion. In other words, after 10,000 years, summer in the Northern Hemisphere will be shorter than they are today, and winters will be longer. Now, what I want to add to this video is that perihelion itself is also changing. So if I redraw the sun, our orbit would look like this right now. And I'll exaggerate its eccentricity to clarify the perihelion and aphelion. So right now, this is perihelion, and here is aphelion. There's also rotation of perihelion, and sometimes this is called axial precession, perihelion precession, or apsidal precession. So if we wait thousands of years, our orbit will look like this. The actual perihelion would have rotated, so our trajectory would look like this. If you wait a little longer, it might look like this. Year after year, you really won't notice the difference. It takes 26,000 years to complete one cycle of axial precession, the change in the direction of the axis of rotation described earlier. 26,000 years from now, our polar will point in the same direction again if the perihelion does not change. We may have completed a total period of axial precession. However, it will take less than 26,000 years for our perihelion date to be what it is today. Earth's apsidal precession cycle is approximately 112,000. This cycle and the 26,000 cycle of axial precession combine to take 19,000 to 29,000 years, an average of 23,000 years to make one revolution around the vernal equinox of the ellipse, i.e., the perihelion returns to the same date. There was a scientist who was well aware that the astronomical factors described above affected the change in incident energy on Earth. He studied the changes in insolation over the past 600,000 years at high latitudes in the Northern Hemisphere by the three astronomical factors. He is Milankovitch. Born in 1897 in the small town of Dalje, Serbia, he died in 1958 at 79. The time he lived was confusing, such as the War of the Ottoman Turk Empire, the Balkan War, World War I, and World War II. He was also captured by the Austro-Hungarian army in 1914 during World War I. Milankovitch has dedicated his life to the study of calculating the Earth's orbit and its effects on climate. The result of the first calculation was the 1920 book Mathematical Theory of Thermal Phenomena produced by solar radiation. In 1941, he published the masterpiece, Canon of Insolation and the Ice Age Problem, 656 pages long. In this book, Milankovitch proposed a theory that the Ice Age occurred in the past due to variations in the Earth's revolution and axis of rotation, leading to changes in insolation. He established this theory at a time when there were no computers. There was not even an electronic calculator. It is only calculated manually for a lifetime. He calculated the insolation at 65 degrees north latitude for the past 600,000 years. The first thing he found out was the eccentricity. The graph shows that the eccentricity was reported at regular intervals between 0.01 and 0.05 for 600,000 years. The second was the change in the Earth-Sun distance in June, or the precession percentage. The precession percentage repeatedly fluctuated from approximately -3% to +3%. The third is the tilt of the axis of rotation, which has fluctuated. The variation in isolation combining these three factors was calculated, and the insolation varied between 400 and 500 watts per square meter. The period of high insolation is the interglacial period, and the period of low insolation is the glacial period. The screen is a graph explaining the essential conclusion in Milankovitch's book, published in 1941. At high latitudes in the Northern Hemisphere, there have been several periods during the past 600,000 years when the incident energy has been significantly lowered. Milankovitch considered that period to be an ice age. It is the color-filled part of the graph. Northern Hemisphere high latitudes are located where large ice sheets form. Dansgaard analyzed the remaining Greenland ice core and confirmed the presence of a blockage. This content is linked at the top right. These Northern Hemisphere high latitudes also produced deep water. This deep water is a significant place that influences the global climate. Please look at the video link to the effect of deep water in the climate. However, the Milankovitch theory received little attention at the time. His book, published at the height of World War II, was not translated into English until 1967, 30 years later. It had been more than 10 years since he'd passed away. His theories came to the fore with Cesare Emiliani's study of seafloor sediments. Cesare Emiliani was the first scientist to develop a method for determining the paleoclimate by analyzing oxygen isotope ratios in seafloor sediments, insisted. How he figured out the paleoclimate is also linked at the top right. Crucially, John Embry, who served as a professor at Columbia University and Brown University, played a significant role. His team analyzed seabed cores in the South Indian Ocean over the past 500,000 years. They found 106,000, 43,000, 24,000, and 19,000 cycles in the sea core geological record. This cycle was in perfect agreement with the Milankovitch theory. The Embry team's thesis was published in 1976, 20 years after Milankovitch's death. Cesare Emiliani, who supported the Milankovitch theory, sent the thesis to Milankovitch in Serbia first when the thesis was published at the end of 1955. Emiliani wanted to let him know that conclusive evidence supported his theory. He was also concerned that Milankovitch was old and his days were short. However, Milankovitch died quietly in his native Serbia in 1958. Emiliani had yet to get a reply. Later, Embry visited Milankovitch's home in Serbia to honor his achievements, and he found a copy of Emiliani's paper in Milankovitch's archives. Milankovitch had obviously read Emiliani's thesis. Scientists later called the fluctuations in the Earth's orbital elements that cause climate change the Milankovitch forcing, after Milankovitch, who developed the theory. Until now, we have examined the astronomical elements that impact the Ice Age pattern and the endeavors of researchers who have revealed them. Please give a thumbs up, subscribe, and turn on notifications.